Here we have it. Today we are learning the fundamental theorem of algebra. Fundamental theorem of algebra, we have fundamental theorem of number theory, fundamental theorem of calculus. You've been doing algebra for a large portion of your life, but you have not known the fundamental theorem of algebra. Fundamental theorem of algebra in kind of very short terms is suppose I have a polynomial x to the fifth. It would have 5 solutions. Now, some of those solutions may be real, some of them may be complex, imaginary, but every polynomial of degree n has exactly n complex solutions. So it could have real solutions, imaginary solutions, complex solutions. Together, those all make up the complex number set. Every polynomial with coefficient a and solutions c1, c2, c3, and c sub n can be written in the form x minus c sub 1 times x minus c sub 2, x minus c sub 3, times x minus c sub n. What that tells us is every single polynomial is, in fact, factorable. You may not be able to see it, but it is factorable. The only change to this is a coefficient of a out front. So it might not be x to the fifth, it might be 2x to the fifth. It might not be x to the eighth, it might be 1/3 x to the eighth. So there may be a coefficient out front. And finally, the other piece, which is really helpful, if a polynomial p of x has solution a plus bi, then another solution must be a minus bi. The conjugate. Complex solutions, imaginary solutions, come in pairs. You never just have one. You're always going to have 2 or 4 or 6 or 8. So we're going to diagnose a polynomial from the very beginning. We're going to look at the positive real, the negative real. We're going to look at the total real. We're going to look at the imaginary, the complex, the choices, and the solutions. How do I determine the number of positive real? How many sign changes are there? 1. By the way, this type of problem we're doing right now is basically a problem pulled straight from your test. You're going to have to be able to do this. You're going to have to be able to do it fast. You don't get a calculator, but this is an excellent type of example. Great. How about the number of negative real? Why? Yeah, p of negative x, it doesn't change, so I have 1 negative real. So how many total real do I have? I have for sure 2. Because if I have 1 positive and 1 negative, that is for sure 2, correct? So I don't have to subtract 2 in that scenario. How many total complex solutions do I have? 4. So if I have a total of 4 complex solutions and 2 of them are real, then how many imaginary do I have? I have 2. We haven't even done anything to the problem other than look at it, and you already know you got 1 positive real, 1 negative real, 2 imaginary, for a total of 4. That's kind of cool. That's like diagnosis right from the beginning. Suppose I were to use the rational roots theorem, my choices would be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16. If you want to go ahead and use the rational roots theorem, go right ahead. I would rather factor if I can. Does this factor? 0 equals x to the 4th minus 16. Or x squared minus 4 times x squared plus 4. Does that factor? X minus 2 times x plus 2 times x squared plus 4. So I have solutions of positive or negative 2, and then x squared plus 4 equals 0. When I subtract, I take the square root of both sides. What do we list there? Plus or minus 2i. Look at how our answer is confirmed from the very beginning. Positive 2 is my positive real. Negative 2 is my negative real. 2i and negative 2i are my imaginary. So you can see how they are all lined up exactly like we want. Those are my rational real solutions. Kind of cool, huh? It all matches up. Confirm your answer. Flip it over. Same thing. Positive real. Negative real. Total real. How many positive real? None. P of negative x would be negative 8x cubed plus 1. How many negative real? 1. If I have no positive real and 1 negative real, how many total real do I have? There's 1. There's a total of 3 complex solutions, so how many imaginary will there be? There will be 2. My choices. One eighth, 1/2, and a 4th. Does that factor? Yeah, it does. Sum or difference of cubes. Cubes factors to, what do you multiply by itself 3 times to get 8x cubed? 2x. And 1 will be 1, and it's going to be plus. How do I figure out the rest of it? Do you remember? Very good. 4x squared, 1. How about the middle? Multiply those two together, you get 2x. Caitlin's talking about the signs at this point. It always ends with a, and this is opposite the other. Looking at that, I could tell what one of the solutions is. What's one of the solutions? Negative 1/2. And that jives with this right here, doesn't it? I got one negative real solution. In order to find these solutions, they're both imaginary, I must use the quadratic formula. Negative b plus or minus square root of b squared would be 4 minus 4 times a is 4 and c is 1 divided by 2a. What do I get underneath the square root sign? Negative 12. Square root of negative 12. Take out a 2i roots of 3. Everything is divisible by 2. So I have 1 plus or minus I roots of 3 all over 2. I'm sorry, not over 2, but over 4. What I didn't show you on the last one, I apologize, is the second part of the fundamental theorem of algebra says that you can write all polynomials in factored form. So the factored form is x minus negative 1/2 or plus 1/2 times x minus 1 plus I roots of 3 over 4 times x minus 1 minus I roots of 3 over 4. We're going to use it, yep. So that's the factorization, almost. If you multiply the x's, you get x to the third, but we don't have an x to the third from the original problem. What do we have? So the fundamental theorem of algebra says that you might have a coefficient out front. In this case, we do have an 8 out front. That's how that problem factors, which looks absurd, but that's what it is. It is goofy. How many goals are you going to score tonight, DeWalt? 3? I saw 3. Saw 3 there. Yeah, okay. All right. All right. Thank you for your honesty. One more example, and then you're going to start doing some work in class. After that work, we got to finish off some examples on the back side. I have positive real. I have negative real. Total real. The imaginary. Total number of complex choices. Solutions. Positive real. 3 or 1. So now we do subtract by 2. We have no way of knowing if there's 3 or 1. This answers the question, why do you subtract 2 each time? It's because of the complex solutions. They come in pairs. So if there is 1, there's going to be another one. There's going to be at least 2. I plug in negative x. I get negative 2x cubed minus 13x squared minus 26x minus 10. So how many negative real solutions are there? There are none. So the total real, 3 plus 0 is 3, and 1 plus 0 is 1. How many total complex solutions are there? There are 3. So suppose there were 3 real solutions and a total of 3 complex, then how many imaginary would there be? 0. Or suppose that there was 1 real solution and there were 3 complex total, then there would be 2 that were imaginary. So those are our options. Oh boy, choices. Ugh. What are my P's? And my Q's are 1 and 2. So give me some choices here. 1, 2, 5, 10. So plus or minus 1, 2, 5, and 10. Plus or minus a half. Plus or minus 5 halves. And then plus or minus the 5 and plus or minus the 1. Those are redundant. Does this one factor? It doesn't. So what do we do? Rational roots theorem, synthetic division. What do you want to try? What should I not try? What would be bad choices? Why negatives? Because there are no negatives, right? There's none. Don't try any negatives. We've crossed off half of our options. Do you want to try 1? Great. 2 minus 13 is negative 11, plus 26 is 15, minus 10 is 5. That doesn't work. Should we try negative 1? No. How about 2? Are you worried you'd make a mistake if you tried 2? If you're worried about making a mistake, you could always use synthetic division, right? And see if you get 0. I'll try it. Two, 4, negative 9, negative 18, 8, 16, 6. Does it work? Shoot. I know none of the negatives work, and I know 1 and 2 don't work. What do you want to do? You want to roll 10? Want to roll a half? Would Gets give you a fraction? Try half. If not a half, then maybe we'll try 5. Who knows? Drop the 2, multiply, 1. Add, -12. Multiply, -6. Add, 20. Multiply, 10. Add, sweet. DeWalt saw. So that means we have x minus a half times 2x squared minus 12x plus 20. Does 2x squared plus 12x plus 20 factor? What can you take out? Take out a 2. X minus a half times 2 times x squared minus 6x plus 10. Does x squared minus 6x plus 10 factor? It doesn't. So what do we have to use? Ugh. Fortunately, you're really good at it, right? Negative b plus or minus square root of. B squared is 36 minus 4 times a is 1 and c is 10. What do you get underneath the square root line? -4. What's the square root of -4? 2i. So we have 6 plus or minus 2i over 2. So we have solutions of 1/2 and then 3 plus or minus I. Exactly like we thought. If we ended up with 1 positive real, you end up with 2 imaginary for a total of 3. 1/2 was one of your choices. No negative real solutions. You can write this in factored form. X minus a half times x minus 3 plus I times x minus 3 minus I. What's the coefficient? 2. All right, flip back to your notes. Liar. Okay. So we're going to write equation for polynomial of degree 3. So we're going to flip it around. Instead of finding the solutions, now you're given the solutions, and you're going to come up with a polynomial. What's that? And actually, this is a lot easier than what we just did. It is. I'll show you. Yes. So here we go. Write equation for polynomial solutions of 4 and I. If 4 is a solution, then what's the binomial that factors into it evenly? Ooh, that was easy. And if I have a solution of I should write x minus I. Oh, it says that there's 3 solutions. I've only got 2. Why? Imaginary come in pairs. So if you have I, you also have negative I. So I'm going to have x plus I. Very good. Now all you have to do is multiply it out. I have x minus 4 there. And here I get x squared. Then what? Plus xi minus xi minus I squared. What happens to the xi's? So you have x minus 4 times x squared plus 1. Notice how we made the imaginary parts go away? Now, just simply multiplying these 2 binomials. X cubed minus 4x squared plus x minus 4. That's our polynomial. Told you, no big deal, right? our last example. Right, equation for a polynomial of degree 3 with solutions of -3 and 4 minus 2i roots of 3. Very good. So we've got x plus 3. We have x minus the quantity 4 minus 2i roots of 3. Alex said if 4 minus 2i roots of 3 works, then so does 4 plus 2i roots of 3. So now we're going to multiply that out. Here he said, I like it. X plus 3. I'm going to raise x minus 4 plus 2i roots of 3. X minus 4 minus 2i roots of 3. X squared. Minus 4x minus 2xi roots of 3. So I just multiplied the x through to each term. Now I have to move on to -4, so it's a minus 4x plus 16. I took 4 times that, no, 4 times that, plus 8i roots of 3. Plus 2xi roots of 3. This times this, yes, 2xi roots of 3 minus 8i. And then I have 2i roots of 3 times negative 2i roots of 3. That's got to be some kind of number, huh? 2 times -2, -4. I times I. Root of 3 times root of 3. Can I get 12? What happens? Negative 2xi roots of 3, positive 2xi roots of 3, gone. 8i roots of 3, negative 8i roots of 3, gone. We got x plus 3 out front. Got an x squared. Got a negative 8x. And we've got a positive 28. Now we've created a problem that you had back in 8th grade, right? X cubed minus 8x squared plus 28x. Now we move on to the 3 plus 3x squared minus 24x plus 84. X cubed minus 5x squared plus 4x plus 84. Okay, the first one was easy. Second one, a little bit more involved. That's how that goes. There's about 3 different ways of doing the problem. I used to try to teach multiple ways. I noticed people got very confused. This is the most straightforward way I could find to teach it. There are other ways to do it. If you're interested, I'll share with you later. Good job.